What if light moved, like a bicycle instead of a rocket? Would the universe look the same if light crawled instead of raced? If light was slower, would we see the past differently? Would time stretch longer, or would space collapse? What happens when the universe's speed limit changes? This isn't just about speed. It's about how reality would fall apart. Let's slow things down. What if the universal constant that governs our reality changed? What if the speed of light, that silent ruler of distance and time, moved just a little slower through the cosmic void? Imagine a single beam of light drifting across the vast emptiness of space, taking its time rather than rushing at its customary 300,000 kilometers per second. Light weaves through everything we know. It defines our understanding of time itself. It creates our concept of distance. It establishes causality, what can affect what and when. The speed of light isn't just a number in a physics textbook. It's the thread that holds our universe together, the unbreakable limit that shapes the very fabric of reality. When you look up at the night sky, you're not seeing stars as they are, but as they were. That ancient starlight has traveled for years, sometimes millions of years, to reach your eyes. The light from our nearest stellar neighbor, Proxima Centauri, takes over 4 years to arrive. The glow from the Andromeda Galaxy began its journey toward us 2.5 million years ago, when our earliest ancestors were just beginning to walk upright. But what if that journey took even longer? What if each photon, each particle of light, moved with less urgency through the cosmic dark? Even the smallest change to light's velocity would transform everything. The universe would still exist, but it would breathe differently. Time would flow at an altered rhythm. Distance would stretch and bend in new ways. The cosmos would reconstruct itself around this new limit, this new pace of reality. As you close your eyes tonight, consider how deeply the speed of light touches every aspect of existence. It determines how quickly the warmth of the sun reaches your sky in 8 minutes and 20 seconds at its current pace. It governs how stars form and die, how galaxies communicate across vast cosmic neighborhoods. It shapes the very possibility of life itself. Imagine if that solar warmth took not minutes but hours to reach us. Imagine dawn slowly brightening, not in moments, but across a full day. The world would still turn, but to different rhythms, different patterns. Our understanding of immediacy would transform. Our experience of presence would shift. The constancy of light's speed has shaped not just physics, but philosophy. We know we cannot travel faster than light. It forms a cosmic speed limit that no material object can surpass. This limitation creates our understanding of cause and effect. It establishes what we can know and when we can know it. It separates the past from the future with elegant simplicity. But if light traveled more slowly, these boundaries would blur. The relationship between space and time would reconfigure. The universe would still follow rules, but they would be different rules, leading to different consequences, different possibilities. In our universe, light travels fast enough that we rarely notice its delay in everyday life. When you turn on a lamp, the room appears to fill with light instantly. When you speak to someone across the table, your words seem to reach them immediately. But these are illusions born of light's tremendous speed. There is always a gap, always a journey, always a delay, just one so brief our senses cannot detect it. In a world with slower light, these delays would become apparent. Conversation might include noticeable pauses as words crossed even short distances. Shadows would linger longer after their causes moved on. The synchronicity we take for granted would dissolve into more visible patterns of cause and delayed effect. Let us drift together through this gentle thought experiment. Not to solve every equation or predict every outcome, but to wonder, what would it feel like if light took its time? How would we experience a universe where the fastest thing we know moved just a little bit slower? What shadows would lengthen? What horizons would shift? What mysteries would deepen if light itself weren't in such a hurry? The speed of light isn't just a physical constant. It's a philosophical boundary. It's the line between past and future, between here and there, between possible and impossible. and if that boundary moved, everything else would move with it. So as you drift towards sleep, imagine that beam of light crossing space at a more leisurely pace. The universe it illuminates would be different in ways both subtle and profound. Some stars might never be seen. Some processes might never occur. Some thoughts might never be thought. But other possibilities would emerge in their place. Other patterns would form. Other wonders would arise. This is the nature of our thought experiment, not to break the universe, but to reimagine it. Not to solve all mysteries, but to deepen our appreciation for how perfectly balanced our reality truly is. Not to reject what is, but to contemplate what might have been if the cosmos had chosen a slightly different path in its earliest moments. What if light was slower? The answer begins with a single beam, taking its time, showing us a different kind of cosmos with each unhurried step. A universe where patience isn't just a virtue, but a fundamental law. A reality where waiting isn't something we do, but something woven into the very structure of existence. As we explore this slower universe together, we'll see familiar objects in unfamiliar ways. We'll reconsider the night sky, the formation of stars, the evolution of life itself. We'll contemplate how our minds might work differently, how our societies might organize around different principles, how our sense of beauty might shift to accommodate new rhythms and new delays. What if light was slower? Let's follow that question wherever it leads, through cosmic history, through imagined futures, through the quiet spaces between stars. Let's take our time, just as light would in this reimagined universe. Let's move at the pace of wonder, which has no universal speed limit. Light draws the boundaries of our perception. It defines not just what we can see, but how we understand the very concept of distance. When we say a star is 10 light years away, we're acknowledging that light itself is our measuring tape stretched across the vastness of space, marking off cosmic intervals with each passing second. If light traveled more slowly, every distance in the universe would feel longer. Not because the physical space would expand, but because the journey across that space would take more time. Imagine if light moved at half its current speed suddenly. Proxima Centauri wouldn't be just over 4 light years away, but nearly 9. The Andromeda Galaxy wouldn't be 2.5 million light years distant, but 5 million. The observable universe would still contain the same galaxies, but they would appear to us as they were much deeper in the past. This is perhaps the most profound consequence of slower light. Our window into cosmic history would shift dramatically. When you gaze at the night sky now, you're seeing stars not as they are in this moment, but as they were when their light began its journey to Earth. With slower light, that delay would deepen. The cosmic story unfolding above us each night would be from a more distant chapter of universal history. Consider our own Sunday. At light's current speed, we see the Sunday as it was about 8 minutes and 20 seconds ago. That delay is so brief that we rarely consider it. But if light moved at just 10% of its actual speed, we would see the Sunday as it was nearly an hour and a half earlier. Dawn would arrive long after the physical position of the Sunday had risen above the horizon. Sunset would linger, with daylight continuing well after the Sunday had physically dipped below the Earth's edge. This delay would transform our experience of time itself. The present moment, what we perceive right now, would be a deeper slice of the past. When you looked at a friend across the room, you would see them as they were a noticeable fraction of a second earlier. At greater distances, this effect would become even more pronounced. A video call with someone on the other side of the world would include a delay not just from processing and transmission, but from the fundamental limit of how quickly light itself could travel. With slower light, the synchronicity of experience that we take for granted would dissolve. Events wouldn't unfold simultaneously for observers in different locations. The universe would feel less like a unified whole and more like a tapestry of overlapping timeframes, each observer inhabiting their own temporal bubble, connected to others only through the patient journey of light. This asynchronicity exists in our current universe, but at scales so vast that we only notice it when looking at cosmic distances. With slower light, it would become part of everyday experience. The rising sun would touch mountain peaks long before valleys. Cities would light up in geographic waves as evening fell. Even sound moving so much slower than light in our world might not seem quite so sluggish by comparison. Perhaps most striking would be our view of the night sky. Stars flicker and shift in brightness due to atmospheric turbulence, but with slower light, they might appear to flicker with the actual variations in their own luminosity, especially the closer, younger stars whose light would reach us within years rather than decades or centuries. The cosmic background radiation, that faint glow from the early universe that permeates all of space, would appear different as well. We currently see this radiation as it was about 13.8 billion years ago, just 380,000 years after the Big Bang. With slower light, we might not see it at all, or we would see an even earlier version of it, from a time when the universe was in a different state altogether. Our scientific instruments, too, would capture a different view of reality. Radio telescopes would receive signals from deeper in the cosmic past. Gravitational wave detectors would register mergers of black holes and neutron stars that happened longer ago. The cosmic narratives we construct from these observations would tell stories of a universe unfolding over longer timescales. In this slower light universe, the practice of astronomy would transform. Watching for supernovae, explosive deaths of massive star astronomers would know they were seeing events from much deeper in the past. The study of variable stars, galaxies in collision, or the expansion of the universe itself would all require recalibration, accounting for the greater lag between event and observation. Even our understanding of cosmic history would shift. The universe is approximately 13.8 billion years old, as measured from the Big Bang to the present day. But the observable universe, the portion we can actually see, has a radius of about 46.5 billion light-years. This difference exists because the universe has been expanding as light has traveled through it. With slower light, this disparity would be even greater. The observable universe would appear smaller, containing fewer galaxies, while the actual universe beyond our visual horizon would be vaster still. Distance itself is partly an illusion, or rather, a consequence of light's finite speed. When we look up at the night sky, we're not just looking across space, but backward through time. The cosmos above us is a living museum, displaying exhibits from different eras simultaneously. With slower light, this museum would contain artifacts from even deeper history, arranged not by type, but by their distance from Earth, each one preserved exactly as it was when its light began the long journey to our eyes. Perhaps there is a beauty in this slower cosmosa universe that reminds us more insistently of its own history. Each glimpse of a distant object would carry with it the quiet acknowledgement: this is not what is, but what was. The cosmos above would feel less like a static painting and more like a narrative unfolding across billions of years, with each pinpoint of light marking a different moment in that grand story. If light was slower, we would be even more deeply time travelers than we already are, our eyes collecting ancient photons, our minds reconstructing worlds that may no longer exist as we perceive them. The star that appears stable in our telescope might have exploded thousands of years ago, its death announcement still traveling toward us at light's patient pace. The galaxy that seems to be colliding with another might have already merged completely, its new form still hidden behind the curtain of time and distance. As you drift towards sleep tonight, consider this: every photon that enters your eye has been on a journey. From its birth in the heart of a star or the filament of a light bulb, it has traveled at the universe's speed limit to reach you. That journey defines not just what you see, but when you see it. If light moved more slowly, the cosmos would still speak to us, but in an even more ancient voice, telling stories from deeper in the past, reminding us with each photon that to look outward is always, inevitably, to look backward. The night sky has been humanity's first calendar, first map, first storybook. For thousands of years, we've looked upward and found meaning in the scattered light of distant suns. But what would that celestial tapestry look like if light traveled more slowly through the cosmic void? If the speed of light were reduced, our night sky would transform in subtle yet profound ways. The stars would still shine, but they would tell us stories from much deeper in the past. The light from Sirius, currently showing us how this bright star appeared 8.6 years ago, might instead show us how it looked 20 or 30 or 100 years in the past. The light from the Pleiades star cluster would reach us not from 400 years ago, but perhaps a millennium into history. Some stars might vanish from our view entirely. Consider those that have already died, exploding as supernovae, or collapsing into black holes. Their final light, the last message announcing their transformation, might still be en route to Earth at light's current speed. But with slower light, that message might never arrive within the lifespan of human civilization. Stars that we can see today might never have been visible to us at all if light moved more leisurely through space. The constellations, those familiar patterns we've named after heroes and creatures from ancient myths, would remain largely intact, as most of their stars lie within a few hundred light years. But their more distant members might be missing, creating gaps in these celestial pictures. Imagine Orion without Betelgeuse, or the Big Dipper missing its handle stars. These altered patterns would have inspired different stories, different mythologies, different ways of organizing the heavens. Beyond individual stars, entire galaxies might fade from our view. The Andromeda Galaxy, visible now as a faint smudge to the naked eye under dark skies, might be too distant to perceive without powerful telescopes if light traveled at half its actual speed. The light that left Andromeda 2.5 million years ago would still be journeying toward us, perhaps arriving only in some distant future era of Earth. Our observable universe, that spherical bubble of space from which light has had time to reach us since the Big Bang, would shrink dramatically, currently extending about 46.5 billion light-years in all directions. This cosmic horizon would contract with slower light. Countless galaxies would slip beyond this boundary, becoming permanently invisible to us, their light unable to bridge the expanding gap created by cosmic inflation and light's reduced velocity. Astronomers speak of the observable universe as a fraction of the actual universe. We can only see those regions from which light has had time to reach us. With slower light, this fraction would become even smaller. Our cosmic window would narrow, focusing our view on the nearer, more recent universe, while the deeper cosmos remained forever beyond our perception. Yet this more limited view would come with an unexpected gift: density. The slower the speed of light, the more concentrated our view of cosmic history would become. Each degree of sky would contain light from a narrower slice of time. We would see fewer galaxies, but we would see them in greater temporal detail, witnessing more of their evolutionary stages compressed into our field of view. This compression might reveal patterns that remain hidden to us now: galaxy formation, stellar evolution. The dance of cosmic structure saw these processes unfold over millions or billions of years. With slower light, we might see more steps in these cosmic dances within a single observational window, as light from different epochs reached us simultaneously from different distances. Our telescopes, too, would peer into a smaller but temporally denser universe. The Hubble Space Telescope has shown us galaxies as they appeared just a few 100 million years after the Big Bang. With slower light, its gaze might extend only halfway to that cosmic dawn, but showing us those midway galaxies in states we can never observe in our faster light reality. The cosmic microwave background, that faint radiation permeating all of space from the early universe, might appear different as well. We currently observe it as it was about 380,000 years after the Big Bang, when the universe cooled enough for light to travel freely. With slower light, we might see this radiation from an even earlier state, or perhaps not at all if that light were still en route to Earth. Night itself might feel different under slower light. The darkness between stars would seem deeper, more absolute. The Milky Way, that ghostly river of light from billions of distant suns, might appear fainter, its more distant regions too far for their ancient light to have reached us yet. The sky would feel more intimately connected to deep history, each visible point a message from further in the past than we can currently imagine. For ancient humans, the night sky was alive with meaning. Stars guided navigation, marked the seasons, and featured prominently in religious and cultural narratives. A sky with fewer visible stars might have led to different navigational techniques, different calendars, different stories about our place in the cosmos. Our entire relationship with the heavens would have evolved along different lines in a slower light universe. Perhaps in such a world, every star would be more precious, its light having traveled even longer to reach human eyes. Each visible point would represent a deeper connection to cosmic history, a more ancient messenger from the depths of time and space. The rarity of these messengers might have given them even greater significance in human culture. What of those stars just now becoming visible? In our universe, new stars come into view as their first light finally reaches Earth, after journeying across space for years, or centuries, or millennia. With slower light, this process would unfold over longer timescales. A star whose light is just now arriving after a 1,000-year journey might, in a slower light cosmos, remain invisible for thousands more years. The sky would evolve more slowly from the human perspective, new stars appearing with less frequency, the heavens more stable across generations. And yet, paradoxically, the stars themselves would appear more dynamic. Currently, most stars change so slowly that human observers perceive them as constant. But if we were seeing them from much deeper in their past, more stars might visibly change within a human lifetime. A star that exploded 10,000 years ago might, in our slower light universe, be just now sending its light of transformation toward Earth. As you rest beneath tonight's sky, consider how the cosmic story above you is written in light that has traveled across unimaginable distances at its universal speed limit. That speed gives us the particular slice of cosmic history we observe. If light moved differently, the book of the heavens would open to different pages, telling different stories, revealing different wonders. The universe would not be less, just differently visible, differently known, differently experienced. The night sky is not just a view of space, but a window into time. And if light traveled more slowly through the cosmic void, that window would open onto even deeper chapters of universal history, showing us stars not just as they were, but as they were in a more distant, more ancient past than we can currently perceive. Our sky would contain fewer stars, but each one would carry a message from further back in cosmic time, a deeper connection to the universe's long evolution toward the present moment. Time and light are intertwined in ways that go beyond our everyday understanding. When Albert Einstein published his theory of relativity in the early 20th century, he revealed a profound truth. The speed of light isn't just a measurement, but a fundamental constant that shapes how time itself unfolds. If this constant were different, if light moved more slowly through the vacuum of spacetime as we experience it, would transform in strange and beautiful ways. In Einstein's universe, our universe, the speed of light creates a cosmic speed limit. Nothing with mass can travel faster than light. This limitation isn't arbitrary, but woven into the fabric of spacetime itself. Light speed serves as the conversion factor between time and space, between energy and matter. Change this speed, and you change the fundamental equations governing reality. If light traveled more slowly, time dilation effects would become more pronounced. Time dilation is that curious phenomenon where time passes differently for objects moving at different speeds or in different gravitational fields. We rarely notice it in daily life, but satellites orbiting Earth must account for it. Their clocks run slightly faster than identical clocks on the ground due to their speed and distance from Earth's gravitational pull. With slower light, these effects would amplify. An astronaut traveling at just a fraction of our current light speed might experience time passing significantly slower than people on Earth. A journey that feels like months to the space traveler might span years or decades for those left behind. The emotional and philosophical implications of such temporal disconnection would reshape how we think about exploration, about separation, about the very meaning of distance. Even modest travel speeds would produce noticeable time dilation. A commercial airplane passenger might land to find that slightly more time has passed for those on the ground than they experienced in flight. Transcontinental journeys could include not just spatial displacement, but temporal shift as well. We would need to recalibrate our understanding of simultaneity, of shared experience, of what it means to be in the same moment. Motion itself would feel different. As objects approach the speed of light, they experience increasing resistance to further acceleration. This isn't due to air resistance or friction, but to the fundamental relationship between mass and energy, the famous equation E equals mc squared, where c represents light speed. With a lower value for c, this resistance would become apparent at slower speeds. Vehicles would encounter relativistic effects more easily, perhaps changing how we design transportation or limiting how fast we could practically travel. Our global positioning systems would need complete redesign. Today's GPS satellites incorporate relativistic corrections to account for time dilation effects. Without these, location errors would accumulate at a rate of about 10 kilometers per day. With slower light, these corrections would be far more substantial. Navigation would require constant awareness of relativistic effects, turning everyday travel into an exercise in four-dimensional thinking. Communication across distances would undergo profound changes. Radio waves, traveling at light speed, currently circle the Earth in about 1/7 of a second. With slower light, global communication would include noticeable delays. Conversations between continents would feel less immediate, more like exchanges of messages than fluid dialogue. The rhythm of human connection across space would slow, perhaps encouraging more thoughtfulness, more patience in how we communicate. The synchronization of time across distances would become more challenging. Currently, atomic clocks around the world can be synchronized with extraordinary precision. With slower light, maintaining a unified global time would require more complex calculations, constant adjustments, awareness of the relative motion between timekeeping stations. Perhaps we would develop a more flexible concept of time itself, one that acknowledges its relativity, rather than insisting on absolute simultaneity. Light's slower speed would alter our experience of acceleration as well. The faster you move, the more your mass appears to increase from an outside perspective, another consequence of Einstein's equations. With slower light, this relativistic mass increase would become noticeable at speeds we can actually achieve. Accelerating a spacecraft or even a particle in an accelerator would require increasingly enormous energy as it approached the new, lower light speed limit. The very fabric of spacetime would curve differently around massive objects. Einstein showed that gravity isn't a force reaching across empty space, but a curvature of spacetime itself caused by mass and energy. The mathematics of this curvature depend on light speed. With slower light, the same mass would create more dramatic curvature, potentially making gravitational lensing effects where light bends around massive objects, more prominent in our observations of the cosmos. Even the passage of time near massive objects would change more dramatically. Currently, time runs slightly slower near Earth's surface than in orbit due to gravitational time dilation. With a reduced light speed, this effect would amplify. Perhaps clocks at different elevations in the same building would tick at noticeably different rates. Mountain dwellers might age fractionally faster than those living at sea level. Not enough to notice in a lifetime, perhaps, but measurable with precise enough instruments. Our perception of causality, what can affect what, and when would need recalibration as well. The light speed limit establishes which events can possibly influence others. Events separated by more distance than light can travel between them cannot have a causal relationship. With slower light, this causal horizon would shrink. Regions of space that could once affect each other would become causally disconnected. The universe would partition into smaller bubbles of possible influence. The relationship between space and time would shift more dramatically as objects moved. Length contraction, the relativistic effect where moving objects appear shortened in their direction of travel, would become more prominent at everyday speeds. A fast-moving train might visibly compress from the perspective of a stationary observer. The shape of objects would become dependent on relative motion in ways we rarely observe in our faster light reality. Perhaps the most profound change would be to our fundamental understanding of time itself. With relativistic effects more prominent in everyday life, we might develop a more flexible, less linear concept of temporality. Time would be obviously relative rather than seemingly absolute. Its flow would visibly depend on motion and position, challenging our intuitive sense of a universal now that connects all observers. As you drift towards sleep tonight, consider how the constant speed of light shapes your experience of time in ways too subtle to notice. It determines which events from the distant universe can reach your awareness. It establishes the causal structure of reality around you. It sets the pace at which change can propagate across space. If light was slower, time would still flow. Clocks would still tick. Days would still pass. But the relationship between different observers' experiences would shift. The cosmos would whisper a different story about how past becomes future, about how here connects to there, about the fundamental nature of change itself. The universe would remain vast and wonderful, but its rhythms would alter, its processes unfold to a different temporal meter, its very fabric vibrate to a changed frequency in the cosmic symphony of existence. The universe we inhabit has unfolded over 13.8 billion years, from the intense heat of the Big Bang to the star-scattered cosmos we see today. This cosmic evolution follows pathways shaped by fundamental constants, including the speed of light. If light moved more slowly through the vacuum of space, the entire history of the universe would be rewritten from its earliest moments. In the first fractions of a second after the Big Bang, the universe expanded rapidly in a period called inflation. This expansion stretched space itself, smoothing out irregularities and establishing the large-scale structure we observe today. The speed of light influences how quickly different regions of the early universe could communicate with each other, establishing what physicists call causal horizons. With slower light, these horizons would be smaller, potentially creating a more varied, less uniform cosmic landscape from the beginning. As the universe continued to expand and cool, it eventually reached a temperature where light could travel freely for the first time, about 380,000 years after the Big Bang. This moment, called recombination, released the radiation we now observe as the cosmic microwave background. With slower light, this crucial transition might have occurred later, when the universe was larger and cooler. The pattern of temperature variations frozen into this background radiation would differ, carrying alternative information about the universe's infancy. Perhaps the most profound changes would come during the epoch of structure formation, when matter began to coalesce into the first stars and galaxies. Gravity pulls matter together, while radiation pressure pushes it apart. This delicate balance determines how quickly cosmic structures can form. With slower light, radiation would exert its influence differently, potentially delaying or accelerating the birth of the first luminous objects. The first stars in the universe, massive and bright, lived brief but crucial lives before exploding as supernovae, scattering newly forged heavy elements into space. The timing of their formation and destruction would shift in a slower light universe. These stellar pioneers might appear later in cosmic history, altering when the universe first became enriched with the carbon, oxygen, and iron that would eventually make planets and life possible. Galaxies too would assemble on a modified schedule. The merger of smaller protogalaxies into the majestic spirals and ellipticals we see today depends on the interplay of gravity, radiation pressure, and the speed at which influences can propagate through space. With slower light, galactic evolution might proceed at a different pace, potentially creating a universe with larger numbers of smaller galaxies, or fewer, but more massive cosmic structures. The distribution of matter on the largest scales could look quite different as well. In our universe, matter forms a vast cosmic web, with galaxies arranged along filaments surrounding relative empty voids. This pattern emerges from tiny quantum fluctuations in the early universe, amplified by gravity over billions of years. The speed of light influences how these initial fluctuations can grow and connect. A slower light speed might create a cosmic web with a different mesh size, different densities, different patterns of galactic clustering. The expansion of the universe itself might follow a different trajectory. Einstein's equations of general relativity, which describe how space expands, include the speed of light as a fundamental parameter. Change this speed, and you potentially change the rate at which space itself stretches. A universe with slower light might expand differently, either more rapidly or more slowly, depending on how other constants adjust to maintain the consistency of physical laws. Even the dark energy that appears to be accelerating cosmic expansion in recent epochs would operate differently. The energy density of empty space and its relationship to expansion depends on light speed through Einstein's equations. With slower light, the universe's fate might change perhaps accelerating toward a big rip where all structures are torn apart, or decelerating toward an eventual big crunch where everything reconverges. The formation of stars throughout cosmic history would follow altered patterns. Stars form when gravity compresses clouds of gas until they become dense and hot enough for nuclear fusion to ignite. Radiation pressure from this newly born star pushes outward, eventually balancing gravity to create a stable stellar body. With slower light, this balance would shift. Stars might need to be more massive to achieve stability, or they might form with different internal structures, burning their nuclear fuel at different rates. Planetary systems would feel the effects as well. As dust and gas orbit around newborn stars, the interplay between radiation pressure and gravity helps determine which particles stick together and which disperse. This delicate dance shapes the formation of planets. With slower light, radiation would behave differently, potentially changing which types of planets form at which distances from their parent stars. The habitable zones around stars, those regions where temperatures allow liquid water to exist, might expand or contract with changing light speed. Since stellar luminosity and the distance at which that energy is received both relate to light's properties, the Goldilocks regions where life as we know it could evolve might be found at different distances, or might be wider or narrower than in our universe. Black holes, those mysterious regions of extreme gravity from which not even light can escape, would maintain their essential nature, but with altered properties. Their event horizons, the boundaries beyond which nothing can return, would still exist, but their size, relative to their mass, might change. The radiation they emit through quantum processes, known as Hawking radiation, would emanate at different rates, potentially changing their lifespans and how they interact with surrounding matter. Galaxy clusters, the largest gravitationally bound structures in the universe, assemble over billions of years as smaller groups merge together. Their formation timeline would shift with changing light speed, potentially creating either more fragmented or more unified large-scale structures. The hot gas between cluster galaxies, which we observe through its X-ray emissions, would reach different temperatures and distributions, telling a different story about cosmic evolution. Perhaps most profoundly, the age of the universe itself might be perceived differently. We measure cosmic age partly by how long light has taken to reach us from distant objects. With slower light, the universe would appear older relative to other temporal markers. The evidence of ancient events would take longer to reach our telescopes, making cosmic history seem more stretched out from our perspective. As you contemplate these altered cosmic pathways, remember that the universe we observe has been finely tuned through the interplay of fundamental constants. Change one parameter, like the speed of light, and the entire cosmic story rewrites itself from beginning to end. Not because any particular value is correct, but because each possible combination of constants creates its own unique cosmic symphony, its own distinct pathway from simplicity to complexity. In this different universe with slower light, time and space would still unfold. Matter would still coalesce into stars and planets. The cosmic dance would continue, but to a different rhythm, following different patterns, creating different possibilities for complexity to emerge against the backdrop of fundamental physical laws. The universe would still be beautiful, still be vast, still be worthy of wonder, but it would be beautiful in its own unique way, vast according to its own measure, wonderful for its own specific complexity. As you drift towards sleep, consider how perfectly balanced our actual universe is. The specific speed of light we observe has helped create the specific cosmos we inhabit, with its particular stars, its particular planets, and perhaps even its particular capacity for conscious beings to look upward and contemplate the night sky. Stars are the universe's hearths, cosmic furnaces converting matter to energy through nuclear fusion. They warm worlds, illuminate galaxies, and forge the elements necessary for planets and life. But their birth, life, and death all depend intimately on how light and heat move through space. If light traveled more slowly, stars themselves would evolve along different pathways. The birth of a star begins with gravity. Vast clouds of hydrogen and helium gas sometimes spanning hundreds of light years, slowly contract under their own gravitational pull. As these clouds collapse, their density increases and temperature rises. But this process depends on a delicate balance. The cloud must be able to radiate away heat as it contracts. If it cannot cool efficiently, pressure builds up, potentially halting the collapse before a star can form. With slower light, this cooling process would change fundamentally. Heat, which ultimately escapes through radiation, would remain trapped in the collapsing cloud for longer periods. The cloud might heat up faster than it could radiate energy away, creating greater pressure against gravity's inward pull. The threshold for star formation might rise, requiring more massive gas clouds to overcome this resistance and successfully birth new stars. Perhaps in such a universe, stars would form less frequently, but tend to be more massive when they did appear. Smaller protostars might never overcome the pressure barrier, remaining as failed stars, or brown dwarf objects too massive to be planets, but too small to ignite hydrogen fusion in their cores. The stellar population would skew toward the larger, hotter, more luminous end of the spectrum. Once a protostar does form, its journey to becoming a main sequence star is stable. Hydrogen-burning stellar adult depends on reaching an equilibrium between the outward pressure of radiation and the inward pull of gravity. Slower light would alter how quickly radiation pressure builds within the forming star, potentially changing how long this youthful phase lasts and what internal structure develops during these formative years. The protostar phase, where young stellar objects are surrounded by disks of gas and dust from which planets eventually form, might extend longer with slower light. These planet-forming disks might experience different temperature gradients, altering where various materials can condense and what types of planets might form at different distances from their parent stars. The architecture of solar systems could look quite different in a slower light universe. When a star finally reaches the main sequence, that stable period where hydrogen fusion in the core creates a perfect balance with gravitate structure, would reflect the altered physics of slower light. A star is essentially a layered sphere of plasma, with energy generated in the dense core gradually working its way outward through radiative and convective zones, until it reaches the surface, or photosphere, where it escapes as visible light and other radiation. With slower light, this energy transfer would proceed differently. The radiative zones, where energy moves primarily through photon diffusion, would become less efficient. A typical photon in our Sun's radiative zone takes anywhere from 10,000 to 170,000 years to complete the random walk from core to surface, due to being constantly absorbed and re-emitted by plasma particles. With slower light, this journey would take even longer. This inefficiency in energy transport might cause stars to develop different internal structures, perhaps with smaller radiative zones and larger convective regions, where energy moves through the physical circulation of plasma. These structural changes would influence stellar lifespans, temperature distributions, and even the fusion pathways that create heavier elements. The surface temperature of stars might run hotter with slower light, as heat would escape less efficiently from the stellar interior. This could shift the characteristic color of stars toward the bluer end of the spectrum. The familiar classification of stars by color and temperature, from cool red dwarfs to hot blue giants, might need recalibration, with perhaps fewer stars occupying the cooler categories. Stellar lifespans too would likely change. A star's life expectancy depends largely on its mass and how quickly it consumes its nuclear fuel. With altered internal structures due to slower light transport, stars might burn through their hydrogen reserves at different rates. Perhaps they would live longer, their nuclear fires burning more slowly and steadily due to changed pressure and temperature gradients. Or perhaps higher core temperatures would accelerate fusion, leading to shorter, more intense stellar lives. The balance of elements produced by stars would shift as well. Different stellar temperatures and pressures create different fusion pathways, producing varying proportions of helium, carbon, oxygen, and heavier elements. If slower light created systematically different stellar interiors, the chemical enrichment of galaxies over cosmic time would follow an altered trajectory, potentially changing the abundance of elements available for planet formation and eventually life. Stellar atmospheres, the outer layers from which light finally escapes into space, would develop different structures with slower light. The temperature and pressure gradients that create features like sunspots, prominences, and coronal mass ejections would adjust to the changed physics. The rhythms of stellar weather, from the 11-year solar cycle to the more dramatic outbursts of variable stars, might follow different patterns or operate on altered timescales. When massive stars reach the end of their lives, they often explode as supernovae, momentarily outshining entire galaxies and scattering newly forged elements across space. These explosions depend on the complex interplay of gravity, nuclear reactions, and radiation pressure. With slower light, the shock waves and energy transport within these explosive events would propagate differently, potentially changing their luminosity, duration, and the mix of elements they contribute to the interstellar medium. Neutron stars and black holes, the remnants left behind by some stellar deaths, would maintain their essential nature but might form under different conditions or with altered properties. The boundary determining which dying stars become neutron stars and which collapse into black holes might shift. The properties of these exotic objects, from their spin rates to their environmental effects, could reflect the slower light physics that govern their birth. Stars don't exist in isolation but interact with their surroundings. They illuminate gas clouds, compress nearby matter with their stellar winds, and influence the formation of the next generation of stars. With slower light, this interaction between stars and interstellar medium would change. Stellar radiation would take longer to reach nearby gas clouds, potentially altering the rhythms of sequential star formation that create the beautiful stellar nurseries we observe. Even the appearance of stars would change to our eyes. The subtle pulsations that cause stars to twinkle when viewed through Earth's atmosphere would be accompanied by actual variations in the star's surface brightness, taking longer to reach us. The dance of starlight would follow a different choreography, combining atmospheric effects with the deeper history of stellar surface activity visible due to light's more leisurely cosmic journey. As you drift towards sleep beneath the canopy of stars visible from Earth, consider how each point of light represents a delicate balance of fundamental forces. The stars exist as they do because light moves at precisely the speed it does no faster. They burn for billions of years, forming elements, warming planets, making life possible, all because of this perfect calibration of cosmic constants. If light were slower, stars would still shine. They would still transform simple hydrogen into the complex elements of life. They would still punctuate the darkness of space with their brilliant presence. But they would do so according to different rhythms, different lifespans, different patterns of birth and death. The cosmic hearths would still burn, but to a different measure, illuminating a universe that remained beautiful in its own unique way. We have journeyed through the cosmic implications of slower light. How it would reshape distance, alter the night sky, transform time, rewrite universal evolution, and change the lives of stars. But what of our own experience? What would it mean to be human in a universe where light took its time? Our perception is built around light's speed in subtle ways we rarely consider. We assume that what we see is what exists in this moment. We trust our eyes to show us the present. But even in our universe, this is an illusion born of light's tremendous velocity. With slower light, this illusion would dissolve. We would become constantly, consciously aware that everything we see belongs to the past, not just distant stars, but the face of a friend across the table, the bird flying overhead, the expressions changing in a loved one's eyes. Communication would transform most dramatically. Currently, fiber optic cables carry internet data around the world at about 2/3 the speed of light, creating delays measured in milliseconds. With significantly slower light, these delays would extend to seconds, minutes, or more. A video call with someone on another continent might include pauses long enough to make conversation feel like sending letters rather than sharing a moment. Perhaps we would adapt, developing conversational rhythms that embrace these gaps. Instead of quick exchanges, we might speak in complete thoughts, offering paragraphs rather than sentences, allowing the other person time to receive our full meaning before responding. Conversation might become more considered, more patient, more complete. The art of listening might flourish in a world where immediate reaction was impossible. Writing might become more valued as a form of connection across distances. Unlike synchronous communication, letters and texts don't require immediate response. They already acknowledge the gap between sending and receiving. In a slower light world, the thoughtfulness of written words might seem more natural, more aligned with the fundamental physics of connection across space. Local communities might gain greater importance as the experiential difference between nearby and distant relationships widened. With significant delays in communicating across continents, the immediacy of in-person connection would become more precious, more distinct from distant relationships. Geographic proximity might matter more, creating stronger neighborhood bonds and more localized cultures. Yet long-distance relationships would still exist, just with different expectations. Perhaps they would develop greater depth, built on patience and anticipation, rather than immediate gratification. The joy of receiving a message from someone far away might be heightened by the awareness of how far their words had traveled, how much time had passed while light carried their thoughts to you. Our psychological relationship with time itself might change. With more noticeable delays between events and our perception of them, we might develop a more fluid concept of now, one that acknowledged its relativity, its dependence on distance, its essentially subjective nature. We might think less in terms of single moments and more in terms of overlapping waves of experience, each traveling at light's deliberate pace. Memory might function differently in a slower light world. We constantly update our understanding of the world based on what we perceive. With slower light, the gap between event and perception would widen, creating a more obvious distinction between what is happening and what we can know about it. Perhaps we would develop more sophisticated methods of prediction, mentally projecting the likely present based on the definite past that reaches our eyes. Patience might become not just a virtue but a fundamental aspect of how we interact with reality. Waiting would be woven into the fabric of experience. The gap between action and observable consequence would widen. The rhythms of cause and effect would slow, stretching the space between intention and visible result. We might become more comfortable with incompleteness, with processes unfolding at their own pace, with the universe taking its time to share its stories with us. Even our bodies might adapt differently in a slower light world. Our neural responses, our reflexes, our entire sensory system has evolved in a context where light speed creates effectively instantaneous awareness of our immediate surroundings. With slower light, different perceptual strategies might prove advantageous. Perhaps we would rely more on prediction, on memory, on non-visual senses that don't depend on light's journey. Consider how our experience of beauty might transform. Sunsets would unfold more slowly as light's delay created a gradual transition across the sky. Distant mountains would be seen as they existed noticeably earlier than nearby valleys, creating landscapes that displayed different moments in time simultaneously. Perhaps we would develop aesthetic sensibilities that appreciated these temporal panoramas, these visible collages of various pasts coexisting in our field of view. Art might evolve along different lines. Visual arts would necessarily engage with the visible delay between object and image. Music might explore the gaps between sound creation and perception, perhaps developing forms that acknowledge the listener's temporal distance from the performer. Dance might incorporate the awareness that movement is seen only after it occurs, creating choreography that played with this inherent delay. Science and technology would face different challenges and opportunities. Astronomy would become more explicitly a study of the past, with the depth of that past more dramatically connected to distance. Physics would develop around the more noticeable relativistic effects in everyday life. Engineering would need to account for the slower transmission of information across even modest distances. Our relationship with other living beings might shift as well. With slower light, we would see animals and plants as they were a moment ago, not as they are now. This slight displacement might make us more aware of the gap between perception and reality, more humble about our ability to truly know another being's present experience. Perhaps we would become more patient observers, more willing to wait for understanding. Spirituality and philosophy might develop along different lines in a slower light universe. The visible disconnect between event and perception might lead to different concepts of reality, different ideas about knowledge and truth. Perhaps we would more readily acknowledge the inevitably incomplete nature of our understanding, more completely embrace the fact that we always see through a glass, darkly. Wonder itself might take a different form. In our world, we marvel at light speed, how quickly a sunbeam crosses a room, how a laser can reach the moon in seconds, how starlight from thousands of years ago can still find its way to our eyes. In a slower light world, we might instead wonder at light's patience, its willingness to carry information across vast distances, despite the time required, its persistent journey through space, regardless of how long that journey might take. What would it mean to be human in such a world? We would still love, we would still create, we would still seek to understand ourselves and our universe. But we would do these things with a different relationship to time and distance, to waiting and knowing, to presence and absence. We would build our lives around different rhythms, different expectations, different ways of connecting across the inevitable gaps that separate one consciousness from another. Perhaps there would be a strange comfort in such a world. The delay between action and perception would remind us constantly that our knowledge is always incomplete, always from a particular perspective, always of the past, rather than the absolute present. This awareness might foster a kind of cosmic humility and acknowledgement that the universe unfolds in its own time, revealing itself to us gradually, patiently, one photon at a time. As you drift towards sleep, consider how your consciousness has been shaped by light's particular speed. Your sense of now, your feeling of connection to distant places, your understanding of how long it takes to know something all. These reflect the specific physics of our universe. If light was slower, you would still be you. But your relationship with time, with distance, with knowing and being known, might unfold to a different rhythm, a more patient meter, a gentler flow from moment to moment in the river of cosmic time. We have wandered together through a universe reimagined cosmos, where light moves with less haste across the vast emptiness of space. We've contemplated how this single change would ripple through reality, transforming everything from how stars burn to how humans connect. As our journey comes to its gentle close, let us reflect on what we've discovered in these quieter cosmic rhythms. If light were slower, the universe would still exist. The stars would still shine. Planets would still orbit. Life might still emerge. But all these familiar processes would unfold to a different tempo, creating a reality both recognizable and profoundly altered. Not better or worse, just differently balanced, differently tuned, differently paced. Perhaps there is wisdom in considering such alternatives. Our universe, with its particular constants and laws, is not the only possible arrangement of reality. It is simply the one that exists, the one that has allowed us to emerge and contemplate the stars above us. By imagining other possibilities, we deepen our appreciation for the exquisite calibration of our actual cosmos. Light speed creates a universe where causality remains intact, but operates within constraints. Events can influence other events only within certain boundaries, determined by how quickly information can travel from place to place. This limitation creates the particular ordering of reality we experience, where past definitely precedes future, where nearby can affect nearby more readily than distant can affect distant. With slower light, these constraints would tighten. Causality would still operate, but within narrower confines. Different regions of the universe would become more isolated from each other, their ability to influence one another more limited by the sluggish pace of information transfer. Perhaps such a universe would develop more diversity, more variation, more distinct regions evolving along their own paths, with less cross-pollination of matter, energy, and eventually ideas. The night sky would tell a different story in our slower light universe. Fewer stars would be visible, each one showing us a deeper slice of the past. Yet those we could see might reveal more of their evolution within a human lifetime, as their light from different epochs reached us in more compressed timeframes. The cosmos would still inspire wonder, not through abundance but through depth, not through vastness but through the richness of history contained in each visible point. Time itself would feel different, flowing less uniformly across space, diverging more noticeably for different observers. The universe would seem less synchronized, less simultaneous. Each perspective would contain its own unique slice of cosmic history, overlapping with others, but never identical. Perhaps beings evolving in such a cosmos would develop a more relativistic concept of time from the beginning, seeing it not as an absolute backdrop, but as a malleable dimension, varying with position and motion. Stars would form through the same gravitational collapse, ignite with the same nuclear fusion, shine with the same converted matter energy, but their internal structures would adjust to the slower radiation transport. Their lifespans might extend, their temperatures run hotter, their elemental production shift toward different proportions. The steady hearths of the universe would still burn, but to a different measure, creating a different mix of cosmic ingredients. The universe's evolution from simplicity to complexity would follow an altered path. Galaxies might assemble in different patterns, structure formation proceed on a modified schedule, the entire cosmic web arrange itself with different densities and distributions. Yet complexity would still emerge. Simplicity would still give way to organization, to patterns, to the rich tapestry of relationships between matter and energy that eventually creates the conditions for life. And what of consciousness? That mysterious emergence from organized matter? Would minds evolving in a slower light universe develop different intuitions about reality? Would they perceive time differently, understand causality differently, experience beauty differently? Perhaps they would accept from the beginning what we have had to learn gradually, that perspective matters, that simultaneity is relative, that now depends on where and how you observe it. If such minds develop technology, they would face different challenges and opportunities. Communication across distances would contain more noticeable delays. Observation of distant phenomena would reveal deeper history. The distinction between here and there would carry more significance, the gap between them harder to bridge. Perhaps they would develop greater patience, greater appreciation for locality, greater wonder at the messages that manage to bridge vast distances despite light's unhurried pace. Our journey through this thought experiment hasn't been about finding precise answers. We haven't tried to calculate exactly how stars would burn or galaxies would cluster if light moved at exactly half or a tenth or a hundredth of its actual speed. Instead, we've used this cosmic what if to highlight how perfectly calibrated our actual universe is. Its particular constants have created the particular reality we inhabit. The speed of light isn't arbitrary. It emerges from the deep structure of space-time itself, connecting electric and magnetic fields, establishing the conversion factor between energy and matter, setting the cosmic speed limit that shapes causality. Together with other constants, the gravitational constant, Planck's constant, the charge of an electronet creates the conditions that allow for atoms, stars, planets, and eventually us. Perhaps the most profound implication of our slower light universe would be philosophical. By imagining reality calibrated differently, we're reminded that the cosmos needn't have been hospitable to our existence. The particular balance of forces and constants that allows for complex chemistry, stable stars, and the emergence of life represents just one possibility among countless alternatives. Our existence isn't inevitable but contingent, dependent on the universe having just the properties it happens to have. This contingency might inspire not despair but profound gratitude. The universe isn't required to support our existence, yet here we are, conscious beings capable of observing distant galaxies, understanding nuclear fusion, contemplating alternative physics. We exist in the brief moment when the cosmos has cooled enough for complex chemistry, but not expanded too much for stars to still shine. We inhabit the narrow band of distance from our star, where water remains liquid. We benefit from the precise strength of gravity that allows for planets without crushing the complex molecules of life. As you drift towards sleep, consider that the real miracle isn't that light might have been slower, but that it moves at exactly the speed it does, fast enough to connect distant regions of the cosmos, slow enough to create the causal structure that allows for complexity to emerge and persist. The speed of light isn't just a measurement, but a fundamental thread in reality's tapestry. woven perfectly to create the universe we inhabit. If light was slower, we might see less of the universe, but we might also see more clearly what we can observe. We might know fewer stars, but know each one more deeply. We might communicate across shorter distances, but with greater intention. We might experience less simultaneity, but more awareness of our particular perspective. We might lose some breadth of cosmic connection, but gain depth of local appreciation. The universe, with its current light speed, has allowed us to evolve, to wonder, to look upward on clear nights, and contemplate our place in the cosmic story. It has created the conditions for consciousness to emerge and ask these very questions. It has woven the particular reality we inhabit, with its specific balance of forces, its specific rhythm of cause and effect, its specific flow of time from moment to moment. Sleep now beneath the stars you see as they were, not as they are. Rest in the knowledge that light has traveled years or centuries or millennia to reach your eyes, carrying ancient messages across the depth of space at its own perfect speed. And as you dream, perhaps you'll wander through alternative universes where light takes its time, where causality flows differently, where reality itself unfolds to a gentler rhythm, different, but no less beautiful in its own unique way. For the universe, in all its possible configurations, remains a source of endless wonder. Whether light moves quickly or slowly, whether stars burn for billions of years or trillions, whether galaxies cluster tightly or sparsely, the cosmos continues its dance. And we are privileged to witness it, to contemplate it, to imagine how it might have been, even as we appreciate how perfectly it is. Sleep now and dream of slower light. Dream of patient photons crossing vast distances without hurry. Dream of time stretching between cause and effect. Dream of a universe that takes its time, revealing its wonders gradually, one ancient light ray at a time.